All right, so here's Module 2 review. It's talking about logarithmic functions. So we remember a couple things. We have growth and decay when it comes to exponential functions. And when it comes to exponential, the inverse of an exponential equation is a logarithm, and the inverse of a logarithm is also an exponential. So it's really important to be able to go back and forth from exponential to logarithmic and from logarithmic to exponential. I promise I can talk. And then we're going to be using the properties of logarithms. Okay, so let's get started. So the first one, it says find the value of x, and how we evaluate a logarithm is we have to think that if the base is 16, it's the inverse basically of an exponential equation. So if I have 2 to the third, that equals 8. So as a logarithm, it looks like this: 2 to the third equals 8. So we notice that we're looking at the base and looking at what it equals, and that's going to be the power, basically. Okay, so here, 16 to the what power would give us 4. So I could write it like this: 16 to the what would give me 4. Okay, well, I know that if I took the square root of 16, I'd get 4, but how do I relate that to an exponential variable here? Okay, so the connection there is that whenever we have something like the square root of x, that's also the same as x to the 1/2. So here, 16 to the 1/2 would be equivalent to the square root of 16, which would be equivalent to 4. Okay, there's also another way that I guess we could do this. If the bases are the same, then the powers could be set equal, if you guys didn't remember that. So another way of writing 16 is we could say that 16 is the same as 4 to the second power. Okay, so 4 to the second power equals 16. We still have the x on the outside, and then over here we have 4 basically to the first. Okay, so we multiply the powers, so that's going to be 4 to the 2x equals 4 to the first. And so now, since the bases are the same, we can set the powers equal to each other. So 2x equals 1, divide both sides by 2, and we get x equals 1/2. So that's another way that you could do the same problem. So in here, x equals 1/2. Okay, next it says put the expression in its most simplified form. So here we have the log. I always like to check, make sure that the bases are the same, because sometimes they like to trick you like that. So the bases are the same, so we can combine these, and the properties of logarithms tell us that we just have to multiply whenever it's addition here. So this is the same thing as log with the base 5, 125, that's a 2, 125, come on, times 9. Okay? So it's not in its most simplified form, so I would just take the 125 and multiply it times 9. Oops, 5, that's a 4, 18, that's 2, 2, and then 11, so 1125. So log 5, 1125. All right, so that's that bad boy in simplest form. Okay, next it says, what is the value of this logarithm? And it looks like we've got division, and then it gives us a couple values. Okay, so what I'd like to do first is take this logarithm, and if you have variables and it's tripping you up, then just put values in. Okay, you could do like 1, 2, 3 or something. All right, so this has a base of m, and then it's being divided. Okay, with division, the properties of logarithms is that we can separate this where we have log with a base m, y. If we subtract log mx. Okay, now it tells us the value of this right here is 2.7. So this, well, not that. This right here is 2.7. So I could say that this is 2.7, and then the y is 1.8. So this equals 1.8, and then from here we just subtract. So 2.7 and 1.8. I know that my answer is going to be negative. So now we subtract. So that's going to be 117. So that's going to be 0.9 here. So negative 0.9. That'd be the answer for that one. Okay. So now this last one, we have an e, and remember, e is an exponential equation. The base itself has a value. So e is more of like pi, where e to the first power is like 2.71 or something like that. So we can relate it as a logarithm, but a natural logarithm. Okay, so a natural logarithm has a base e. So anyways, let me just rewrite this down here because it seems kind of cluttered here. So I've got e and then 7x equals 52. Now if you guys remember, whenever we're dealing with an exponential equation and we have a variable up in the exponent, we can't divide, we can't use the methods that we're used to get the x by itself. So what we have to do is convert this into a logarithm, and in this case a natural logarithm. So the base is going to be e, so natural log with base e, this is going to be right here, 52, and then equals 7x. Okay, so x isn't by itself, so in order to get x by itself, I'm going to divide both sides by 7. So in your calculator, you're going to put this natural log of 52 divided by 7. And I'm going to grab a calculator real quick and see if I can calculate that. So let me do natural log 52, and then divided by 7. And I got 0.564. So that would be the answer for number 4. All right, number 5, it says the solid curve in the graph, which is shown right here, is the function f of x, which is the natural log of x. Now, the natural log of x, even though the base isn't shown here, we can safely assume that the base is e. Now, if you were to take in your calculator e to the power of 1, you would actually get a value, get 2.71. So we could go to Desmos and check it out. And what you have to do here is, even though there's no values that are indicated, you have to see which graph over here, and it says select two that apply, which two graphs would best represent the g of x function right here, which is right close to it. Okay, so you want to recall a couple things when it comes to translations, basically, with functions. So we see that we have a logarithm and another logarithm. So whenever we have base 2, okay, we know that at, well, this point that's right here, anything to the 0 power is 1. So that means that when the x value is 1, it's going to be 0. Okay, now that's going to be the same for both of the logarithms and most of the natural logs. Okay, whenever they have a 1 out here, it's like either -1 or +1. That's going to be shifting the graph to the left or to the right. So we know that it's going to intersect here. Now we want to know which values would start to go higher than just the natural log of x. So I've got Desmos, so I'm going to pull that up. And here's the natural log of x right here. So we know that if we were to do basically e to the first power, okay, so if we're going to have e to the first power, we know that that's going to hit at 2.71. Okay, now I don't know if I'm going to be able to get it, but just trust me, okay? 2.71, it's going to be right there at 1. Okay, now if I look at log 3, I know that log 3, it's going to be 1 when it's at 3. Okay, so that means it's going to be a little bit lower than this graph right here. Okay, and as we go along, I mean, you can kind of see that it's going to be below the natural log. Natural log is the one that's in black. Okay, so that's that. And then if we have natural log, and then we have -1, we know that that's going to shift the graph to the right one, so it can't be this one. And then here, whenever the number's on the front, that means that we're going to have some sort of a vertical shift. So this one goes up, okay, so this is good. This is increasing, it's going above. And now when we look at log 2 is, so when the y value is 1, that's when we have basically 2 to the first power. Is that what I'm trying to say there? Okay. So 1's right here. 2 to the first power is 1. So it's above the graph just slightly. Okay, so this is looking like a pretty good candidate for that. So let's keep going. This one is +1, so we know that that's going to shift backwards. And then the next thing we have these two right here. Okay, so this one is definitely, this is whenever you have the number that's on the inside with the variable, that's going to be squashing the graph. So almost like if you were to take this side and then put it in a vise or like a compressor, and it starts to push this way, you're going to see that it rises up a little bit. Okay, so I don't think it's this one. I think the log 2 was pretty dang close. And then if anything, since it says to choose 2, I would say that the natural log with the 3 on the outside. Those are the two that are going above. And since it's not indicated in the PowerPoint, I would say that it could be either C or D, since we have to select 2 that apply. All right, number 6, it says the function, and it gives an exponential function here. We can tell it's exponential because we have the variable up in the exponent. And then the b term is 1/2. Now, since it's less than 1, we know that this will be exponential decay. So I would just pick a couple values like in a t-chart, start substituting in things. So if we, because that's what it's asking, it says create the graph. So this, if you put in 0, that's going to be 0. Anything to the 0 power is 1. So 10 times 1. So that means when x is 0, it's going to be all the way up at 10. Okay, and then try 1, then try 2, then try some negatives, and you're going to find that the graph looks something like this. Notice that it's decaying, and then it's intersecting right here at 10. All right, now you remember this. Okay, these are our rules when it comes to our properties when it comes to logarithms, and one of the most important is not only just being able to convert from log to exponential, but also this change-based formula. We're going to be using this. Okay, whenever we have a base, we could rewrite a base that's different than 10. We could rewrite a logarithm where we put the base on the bottom and then whatever our logarithm is equal to up at the top. Okay, that's going to be useful for the next couple questions. So this word problem, it says the company deposits 25 grand into the bank, and then it starts to say a bunch of stuff. It gives you an equation, and then it says how long will it take, T, to have the account value 30,000. Okay, so just substituting this into this formula without looking at this, this is basically what we're looking at. How long is it going to take for us to make $30,000 if we started off with 25,000 and then we have this formula? Okay, so do you see T? We need to get T by itself. Okay, in order to get T by itself, we first have to isolate the E, the base here. So we're going to divide both sides by 25,000. And then instead of dealing with this, we can go ahead and divide that. And then at this stage, we're going to then convert this into a logarithm. And since we're dealing with E, it's going to be a natural log. So I'm going to write natural log with base E, but we don't have to put it. And then 30,000 divided by 25,000 is 1.2. And then whatever the power is, that's what goes right here. Now the T is not by itself. So what we're going to do then is divide both sides by this decimal. Okay, so I have the natural log of 1.2 divided by this, and then we have our T. Now, I wouldn't figure out what this is because that's not what the question is asking. The question is asking, if you have this, what is the value of K? So here we see that the value of K in this case is going to be 1.2. So that would be your answer. K is 1.2. Okay, next one. It says a large online video game tournament, okay, has this many teams. It says the number of teams, which represents T, remaining after each round. Now I think on your some of your guys' copies, this needs to be an R. Okay, so make sure you double check that. And then it says 8 teams will advance to the quarterfinals. So if the teams are 8, we're going to go ahead and substitute that into this equation. We're not going to look at this yet, okay, so don't freak out. We're going to substitute in an 8 for T, and then this is the equation we have. All right, now do you see how where we need to get to is where R is by itself? So we need to get the power isolated. So one of the first things that we're going to do is get rid of this 65,000. So we're going to divide both sides by 65,000. We have the base by itself. Now we can convert it into a logarithm. So remember, the 1/2 is the base. So when I convert this into a logarithm, the 1/2 goes right here, and then whatever the answer was, that's right here. Okay, so at least we have logarithms, but this one it's split into 2. And now do you guys see how the 1/2 is on the bottom? It's almost like they put the base on the bottom. So if you recall, whenever we're doing change base formula, log 1/2, the base, is going to be on the bottom, and then whatever's in the numerator, whatever's right here is going to go in the numerator. So it's going to look a lot like this. Now I know this is complicated and it looks like cluttery, okay, but we're starting to make it look like what it's trying to ask us to make it look like, okay? So at this point, I see that our denominator looks the same as this one. And then over here, well, we need to figure out what the K is, right? That's the K. Okay, and so the answer isn't necessarily the 65,000 because you see how this one has an 8? Over here, this has a 1. So that means that we need to reduce this fraction where the numerator is 1 and then whatever this will equal. So how do I make 8 into a 1? Well, we'd have to divide by 8. So the 65,000 we're going to have to divide basically by 8 in order for this to be a 1. So 65,536 divided by 8 gives us that. So then that means that's what our K is. So K equals 8,192.